Hello and welcome to Calculus1. So we already talked a little bit about calculus before we started the stream, and I already said that calculus consists of three parts: limits, derivatives, and integrals. The first concepts that we figured out were derivatives, and then integrals, and then limits at the end, which gave us rigorous definition for both derivative and integral. Now we'll cover all of that stuff, but since limit, even though the limit was the last to be mathematically defined, we will start with limits because those are the building blocks for derivatives and integrals. So today we talk about the idea of the limit, and we will be later computing the limits. And then if we have time, we'll get into asymptotes and those kind of things. So first of all, most important, what is the limit? And the idea of that, do you know the answer?
Yeah, it's a bit close, but when x approaches a certain value, what the y value approaches.
Yes. So the limit is, very good, the limit is a fancy way to compute the y value. So you know how, in pre-calculus, you learned how to compute a value of a function. If the function f of x was given to you as x squared, then f of 3 was 3 squared, which was 9. The limit will give you the same answer, 9. But the limit is far more powerful way to compute than plugging into the function. And we're going to discover that soon. For whatever reason, the book has the actual definition of the limit in the last section. So we will cover the rigorous definition of the limit in 2.7. Maybe tomorrow, maybe on Thursday, probably Thursday. But today, we are going to say that the limit as x approaches 3 of x squared is 9. Now, you might be tempted to say, well, yeah, 3 squared is 9. That is the old way to compute. Limits are much more powerful than computing a single point in the function. Limits actually compute infinitely many points around 3 and never compute at 3, because 3 might be excluded. And we still get the answer even if it is, if you use the limit. So now let's see how that works. We will have a graphical approach and then approach with a chart. So here I have our good old x squared graph. And let's say number 3 is, well, it's not, let's say it is right there. So now, what does it mean to approach 3? Well, that means walk towards 3. So I'm going to just put one more line here so I can easily determine the y value. And please look at the screen. You can write this later. If I approach from the left, that means I am walking on the line towards 3. I started walking at 1, walk through number 2 to get to location 3. That motion of me walking on x-axis translates to walking along the function this way, which clearly translates to walking up on the y-axis. So all of these motions, 3 motions, are happening simultaneously, where as you are walking towards 3, you are clearly walking up the line, which means you're walking up the y-axis. If you approach from the right, you will be walking towards 3, let's say starting at 5, walking through 4, and then getting to 3. That means that you are walking down the line and down the y line, and you see how the red and blue converge towards 3, but at the same time, they converge at 9 as the answer, as the y value on the y-axis. So what is the limit of x squared? As x goes to 3, the limit is 9. Now, I never computed 3 squared is 9. What I did is I computed all of the values around 3. Now, that's best seen in the chart of values. So I will say that this is that number 3, right? Those are x values. And I'll pick 3 numbers on the left and 3 numbers on the right that are approaching 3. So say 2.9, and then 2.99 is closer, and then 2.999 is closer still. Over here I can be, let's say, 3.1, then 3.01, and 3.001. Now, compute x squared at all of these values. You will see that the values from this side will go and point towards number 9, and the blue values from the right will also go and point towards 9. So take your calculators and square each one of these values. You will see how from the left they grow into 9, and from the right they fall into 9. But there is no ambiguity there. It will be clear as the sun that it's going to 9. So that's the first thing. Take a calculator. You have cell phones, so just don't be lazy. You can flip the cell phone and get the square if you don't want to type 2.9 times 2.9. And even iPhone can do it if you flip it to the side. That's number 1. You want to take tabs? What? You want to take tabs on my Apple page this semester? Apparently, I reached 350. So yeah, 350 bad comments about Apple this semester. So I think I can beat that. Apple is a company, which includes everything.
Yeah. Apple phones are fine.
Or as the entity, as the image, and yeah, but we'll hold off day one. You want to waste the class and talk about?
Yeah, I was gonna say like maybe next class.
What do we have for 2.9 squared?
8.41.
8.41. And then we have?
8.9401.
Perfect. And then?
8.9401. I'm sorry. I had 8.9943.
Okay, perfect. So you see how 8.4 went to 8.94, 8.994. So clearly goes towards 9. How about 3.1? And then next one? And the next one? So you see how this one is, again, the numbers are getting smaller, pointing to number 9. We never used 3 to compute. Now, why is that significant? Well, that value on the graph might not exist. That could be an open circle. If this is an open circle on the graph at 3, 9, the pre-calculus calculation would return does not exist, right? But the limit will still say 9, because limit computed everywhere else except at 3. So limit doesn't care that that point is not there. So I would like you guys to embrace the limit today as just a new fancy way to compute function value. In the end, that's all it is. You are computing the y value from the given function. But it's so much more powerful than just plugging the number in, and because of that, we can use a lot of other stuff. Like we can define asymptotes, we can define many other things later on, improper integrals, and then eventually derivatives, integrals, and everything else. So as limits are extremely, extremely powerful way to compute. So now you understand how to find limits graphically and using the chart. Believe it or not, that's it for 2.2. Now let's do more examples. But that is what we actually have. Now observe that I have red and blue arrows. Red arrows are all approach from the left, and you can either visually approach or you can approach number-wise. And then the blue one from the right. Sometimes these arrows, when transferred to the y side, will not end up at the same point. Now we know that for function, in order to have a function, we have to have a unique assignment between x and a y. Now, we will be computing two different y's for the same x, which means the limit does not exist. So we have to be careful what type of configuration we have. In some cases, in some calculations, limits are not good to be used, like tax brackets. But for others, limits are great to be used, like a broken bridge with a section missing, or a pothole. So we are going to understand now a different scenario. So say that I have a piecewise function. Say this function is flat up to number 1, and then it picks up here and does something. So this is your function. Is it a function? Yes. It's not continuous function if you know about continuity, but it doesn't matter. Many functions are not continuous. They're still functions. This is called a piecewise function because you have one equation explaining or modeling the line up to 1, and then a different function modeling after 1. But altogether it's called the piecewise function, and it will have two different parts there. Now, do I have f of 1 defined in this case? Do I? Yes. What is it? It's whatever the dot is, which is 2. So it's clearly defined because I do have a point. Now, if both were open circle, then no. But since one is a closed circle, I do have a point there. Now, what happens is I go and I say, do I have a limit? So this is what and careful with the notation, guys. This is new now. X approaching 1 from the left. I'm putting this red minus here of this function. Well, as I'm approaching from the left, what is the y value that I'm getting? I'm getting 2. Now, what is happening as I am approaching from the right, which has this blue plus as a notation? I'm getting 4. Very good. So you will always ask yourself, what is the value that you are getting, the y value that you are getting as you are approaching the x that you need? So you see that the approach from the left gives us 2. Approach from the right gives us 4. Is that unique? 2 is the y value for this point here, and 4 is the y value for this point here. So Both of these together say that the overall limit as x approaches 1 from both sides simultaneously does not exist. Two different values. Yep. One side says it's 4, the other side says it's 2. So which one is it, right? You can't have both of them. 2 and 4 are not the same location. Two more examples, guys. And then we are going to write the theorem, and then we're done. The next example is going to be good old function y equals 1 over x. You better know how to graph this from yesterday's class. X and a y. So now, if you look at this, what's happening with f of 0? Yes? Yeah, but is there a value there? What's f of 0 equal to? Undefined. Very good. Does not exist, or undefined. All right, so now I want to know about the limit. X approaches 0 from the left. What do I get? Negative infinity is correct. Observe that as you're approaching from the left, your y value goes down into negative infinity. So as you're approaching from the left, the y value goes down there. Great. What's happening for the limit x goes to 0 plus? Positive infinity. Very good. The blue approach from the right is going to push up to positive infinity. Great. What is the overall limit for 1 over x as x approaches 0? Does not exist. They are not the same. Right? They diverge from each other. Perfect. Final example. F of x equals 1 over x squared. Now you might have some trouble graphing this because you might have not used this before. Looks like this. What is the f of 0? Does not exist. Very good. What is the limit of 1 over x squared as x goes to 0 minus from the left? Positive infinity. Very good. What is the limit of 1 over x squared as x goes from the positive 0? Positive infinity. What's the overall limit? Aha! See that? You guys are becoming experts here. So we have one-sided approach to tell us whether limit exists or not. And this is very simple. This is where the learning happens now. This is what you learn and remember. If the both one-sided approaches are the same, that's your limit. If they are different, limit does not exist. You will use that to solve every limit you see. Now, all of that is put in a theorem called Theorem 2.2. You don't have to remember the numbering of theorems and stuff like that. But the Theorem 2.2 says if the left and the right approach limits are the same, overall limit is that value. If they are different, limit does not exist. Remember yesterday that I said I will talk about definitions and theorems today? Well, this is it, guys. You're in Calculus 1, and you have to understand that the way to solve problems in calculus is to learn the theorem, because theorem is how you solve problems. Definition is what the concept is. So, the simple example for you guys to understand is this. This is a marker and it dispenses ink. That is the definition. You all know what's going to happen if you touch it, right? The hand. You know its name. And I said this is, so you have the image associated with it. That's the definition. Definition tells you what the stuff is. We are going to learn the definition of the limit in 2.7. Theorem is how to use it. I can say uncap, tip towards the surface you want to write on, and then go at it. That's the theorem. So definition is what it is, and the theorem is how to use it. Now, for all of the calculus from today on, Calc 2, Calc 3, if you don't know the theorem, you don't know how to do the problem. It is impossible for us to cover every single situation, every single problem. In pre-calc was easy. You're learning exponential function. So what do you have? You have 2 to the x, 3 to the x, e to the x. Big deal. Limits are done for trig, for exponentials, for logarithmic, for polynomials, for, right? And those are just some basic functions you learned so far. There's no way in hell that I can go through every single example and tell you this is how you use it for ln, this is how you use it for this, because that's not how you learn calculus. In calculus, you learn the theorem, which is this left-right business, and you apply that to whatever you see. So that's where you are going to have this course much different than your previous courses. That's why you have the class prep, which some of you did, and the class prep contains those theorems and definitions so that when you see a problem, you are able to do the problem. So now let's write the theorem. Yes?
Can you physically hand in the class prep?
It's right here on the pile.
Can we hand it to you?
Right here. The theorem, it has the name 2.2. We don't care about that. We'll just say if limit x approaches a minus of f of x is the same as the limit x approaches a plus of f of x is equal to some value L, which is the limit, then the limit x approaches a of f of x is L. Otherwise, limit does not exist. There you go. That's a theorem. Now, you have to learn how to read this and how to understand this. This part says limit approaching from the left. This part says limit approaching from the right. If they are the same, being a number, say 13, then, so if they are the same, then, right, the limit is that value. See, I'm using the same L. So if this is 13, this is 13. Otherwise, meaning if they're not the same, the limit doesn't exist. And it's as simple as that. You spend time, you read and understand the theorem. Now, this is not an honors option of the course, so we will not be proving these things. But there is a proof for this as well, which says no exceptions. It's valid all the time. That's why it's theorem. So, you spend time to read and understand. And if you don't understand, this is where you need to ask me. Because from that point on, there will be problems that you will not be able to solve. Or you will be solving them incorrectly without knowing. So that's the theorem. And now we apply this theorem on a random question which could be similar to the exam question. For instance, There we go. So I made up whatever. This is my function f of x. And now I have questions. The question number 1. What is the limit as x approaches 1 minus of f of x? Note that you don't even know what f of x is. I never gave you functions for this. Number 2, what is the limit from the right? And the number 3, what is the overall limit? I gotta write it here. And then we have question number 4. What is the left limit? X goes to 4 minus, right? Left limit. Number 5. Limit x goes 4 plus. And overall limit. And then write your own questions underneath for at 7. Left, right, overall. And then you populate these. All right. You bored? No? Who's bored? Go.
Oh.
Right there. Hmm?
What? Oh, never bored.
Never bored?
Something's old. Was it like 2?
Yeah, Brian's got this.
Can't read that.
Standard
Is this
limit.
just like
Overall.
Oh, overall.
Perfect. All right,
So,
give the chance to someone else.
yeah.
All right, who said was bored? You're bored? Awesome. That's why I love my job. You didn't have to do it. It's a good question. Now I gotta do stuff. Great.
Right here, is this just like
It's
I
1, 2.
wasn't sure if you had different.
1, 2, 3, 4.
It's not usually going to be like oh, that's actually 1.99. We didn't notice it.
Yeah, exactly.
Actually, the 2.
So we all have the first 6 questions, correct? Right? All right. Now let's see who else is bored. Who looks bored? Ryan, you look bored. You got the last of 7. Of course you got this. It's good. So they're not written. You can just write on the side somewhere. Limit. What do you? The approach is what value? That's the value of the function. These are the values you're computing. So they go here. 1, 2, 3, 4. So, all right. So limit from the left is how much? 5. Limit from the right? 5. Overall limit? 5. Great. So limit from the left was 5, limit from the right is 5, and because they match, overall limit is 5. It's 5 on the y value, right? So perfect. Okay. Now let's talk about this.
It doesn't have to. It's just what did you realize?
I'll write these on the tablet. Okay, so let's take a look together real quick. The first set over here from the left is 2 because that's the elevation. It's at 2. Y is equal to 2 for this open circle. The next value is 4 because a Y value for this closed circle is 4. Both of those were at 1. Because they don't match, by previous definition, does not exist on the overall limit. Moving to the next set of questions, approaching from the left, which was the red approach, is 4. That's this guy. Approaching from the right, you go down the line, you end up at 3, which is this open circle. And because they're different, by the theorem, does not exist on the overall limit. Which leaves us with what's happening at 7. If I approach from the left, I will go up the line and I'm getting this value, which is 5. If I am approaching from the right, I am going up the line from the other side and I'm also getting the same value, which is 5. Limit from the left and limit from the right both happen to be 5, so the overall limit is 5. Function value is 2. Limit cannot detect that because limit does not compute at 7. Limit computed infinitely many points around 7 from both sides and got 5 every time. Now, the fact that the point was dislocated, limit cannot detect that. So that's what is detected with pre-calculus calculation when you plug the value directly into the function. So the last set of questions, 7, 8, and 9, limit x approaches 7 from the left of f of x is 5. Limit x approaches 7 plus, which is from the right, is also 5. And finally, limit x approaches 7 from both sides simultaneously is 5 because these two were the same value. I will write that f of 7 is 2 because that's where the function value is. Function value is at 2. And that takes care of this. Nice. Questions, concerns? Yes?
That's a lot easier than it sounded in the book. When I read it, I didn't, like, what?
That's why they pay me $7 million.
Nice.
In yen. Oh, you're... Can you please tell them that I'm locked out? I'm locked out. Yeah, you're in charge of the computer for today only. My password is working for tomorrow.
I know, me too.
All right. Yes.
So, good question. So, when we, for 7, whenever it's coming from the minus side, it's 5, right?
Yes.
But how did we get to plus and then it was 5 also?
Because it goes into the same open circle on top.
Oh.
Open circle on top is where both lines feed, right?
Yeah.
And that's at the elevation 5.
Oh, okay.
The function value is at 2. So homework examples in a textbook, number 22, 23. Those would be the examples that are similar, and 24. Those are the examples that are similar to this that you might want to look at and practice to get the concept of the limit down.
22, 23, 24.
Yep, 22, 23, 24.
Wait, Nick, are we doing this wrong?
No, I was just trying to see if, so believe it or not, I hope you're not disappointed, but that's 2.3.
That's 2.3.
Yeah.
All 2.3?
No, 2.2, sorry.
Oh my gosh.
2.2.
So good.
Now we're going to move to 2.3. I will restart the stream, so we have a new title for that.